Hi to everyone. Today we are talking about mainly the solar system, and in particular the barycenter of the solar system. First of all, I'm not an expert of astrophysics. Um, I know nothing about astronomy and such things. I know something about math and physics. So today we are talking on basic concepts, basic ideas. So let's begin about the barycenter of the solar system. What we mean about barycenter? Well, is the central mass of two more bodies, of course, and here we can see some animated images about the motions of two bodies and their barycenter. Well, the most basic model for the solar system we can conceive maybe is the one where the sun is on the center and all the planets moves around it in a circular-like shape. They are not actually spherical, so they are similar. They are actually elliptic, and not only this, but also the mass of the bodies influence the motion of the sun. Of course, we expect that the real behavior is something like this, about maybe the Earth moving around the sun. Okay. This is the barycenter. The barycenter actually is the center of mass. So if we see the definition of the center of mass, the center of mass is defined the point with the coordinate r. This is bold r, so this is a vector. Also, this one is a vector. Actually, is a mean, is a weighted average between the coordinate of the points. We have n points with coordinate ri, and each with a mass mi. So is a weighted average over the masses. Okay. Well, let's make some considerations about the solar system and the barycenter of the solar system. So this is the sun, and we can consider some planets that are moving around the sun. So maybe this is Mercury, this is Venus, and this is the Earth. That they are moving around the sun. Okay. So every planet is its mass. So initially, you can the first model I was thinking about earlier was the model where the barycenter is actually on the center of the sun. This is the most basic model we can make. How actually this model is wrong? Let's consider a limit case. A limit case where all the planets are aligned. Okay. This is of course not realistic. Maybe can be a conjunction over the millennia, but actually is a limit case. So limit case, what I mean about limit case, it's where the barycenter, the center of mass of all the solar system, the actual center of mass of the solar system, have the greatest distance, this distance here, the greatest distance between the center of the sun. Okay, so when all the planets are aligned, this distance is at its maximum, because if we have, for example, this is Jupiter, which is maybe over here. Okay, this is Jupiter. Maybe there's the case where Jupiter is here, so the center of mass is not this center of mass here, the milli-limit one, but is more like here, because there's the influence of this planet on the other side. Well, actually, this one here now it's bigger than the Sun, of course. Maybe it's like this. Okay. So, and this distance here, in this case, this one here is smaller than the distance when the Jupiter is considered here. Okay, this distance here, the limit distance. Okay, so we are thinking about the maximum distance of the actual center of mass from which point? From the center of the Sun. So let's try making some calculations. First of all, let's retrieve some data. Okay, here we are some important data to evaluate the center of mass, in particular the mass of the main planets and their distance from the Sun. Okay, let's retrieve also data for the Sun. Okay, solar mass is this number here. Okay, so let's make some considerations. So we have some masses, and in particular the mass of the Sun, which is 1.99 to the power of 30. In this table here is 10 to the power of 24. So let's convert that we have all this data in this power here. So it's 1 point. Let's copy it. Actually, let's copy from here. Okay. Which is the this number here, to the power of 24, right? 24. Let's check 24, 25, 26, 27. Okay, now it's this way: 24, 25, 26, 27, 28, 29, 30. It's correct. Maybe yes. Okay, let's continue. This is the mass of Mercury. So this is Sun. Let's this is Mercury. And okay, continue. Actually, we can make my best to let's check if this works. Maybe it works in this way. No. I have some problems with Python. I'm more used about I'm more used in programming C++. Let's try this way. Okay, this works. Perfect. And these are the planets. Okay. This is the vector of mass. Okay, so for the calculation of our center of mass, we have this vector mi. Now we need this vector ri. Of course, this is a vector of vectors, because this is a position vector r. But in, considering all the planets on the same x-axis here, this axis here, the position vectors actually are this coordinate here, so they are not vector. We can consider them as scalars. Okay, so we have this scalar quantity here, r, is a list. So distance from the center of the... Okay, so of course the first one is 0, because this is the position of the sun. Okay, so is x equal to 0. We need now the position of the distances between the sun and all of the planets. Okay, so copying this row here, distance from the sun. Okay. This is there's a small comment here. Of course, this is the moon. Maybe it's an average. Of course, actually, we are approximating, but of course, this is what we are calculating here is the barycenter, aka the center of mass here. That is a weighted average, weighted over the masses. So, since the mass of the moon is very small here, this is an approximation, but doesn't affect very much the final result. Actually, all this calculation we are making here is very approximate, because we are considering a limit case, the case where all the planets are aligned. That is like once in a, I don't know how many years, but actually not a realistic scenario. Of course, here we have okay, this is R and R. So now we have two lists of numbers, of 11 numbers, 10 planets plus the Sun. 10 planets if we consider Pluto a planet, of course. No bothering to discuss here about astronomy and astrophysics. As I said before, I'm not an expert. Well, let's actually evaluate the center of mass. Okay, so we start with a for loop with this mi for mi in m. Maybe it works. Let's see. If we make some. I'm not an expert of Python. I'm a beginner. So actually, we check if everything is okay. Okay. First thing, these are all quantities that are considered elevated to the power of 24. So this is implicit in these numbers. First consideration. So okay. Let's make a brief check on this. For example, here the solar mass. The solar mass is about 300,000 times the mass of Earth. Let's check if we make here some checks. Always check your code because mistakes are everywhere, of course. Let's print the mass of the Sun, which is m0, divided by the mass of the Earth, which is the third planet. Actual, the third in vector, because it starts from 0. So if we make the code here, of course, this matters. It's like about, yes, 3,300,000 times. This is approximate because maybe this number here is about, yes, it's approximate. Or 147 times the mass of Jupiter. Let's check. It's almost free. We are only using some electricity and internet connections, of course. The mass of Jupiter. Jupiter is the 1, 2, 3, 4, 5, the 6th planet. Okay, the 6. And if we run the code, this is like about, okay, 147. 147. Actually, in this table, 7.6, I would rather round about 1048. In fact, if we round, okay, if we round in this way, Okay, it's like 1048. It's an approximate. Okay, maybe also these numbers here, of course, are approximate. We can say that even for the significant digits. Okay, I don't expect that the mass of the Earth is like all zeros after this 7, of course. Okay, let's continue our very simple calculation. So we have the barycenter B, or center of mass, Cm, equal to 0. And here we are using this formula here, center of mass, which is the summation of, let's make it this way, okay. We have sum 1 equal to 0 and sum 2 equal to 0. This one is the numerator, and this one is the okay, so this sum 1 is plus equal, so sum 1 is sum plus mi, so if we make it this way, I don't know if it's working this way, so actual mi times ri. Let's check, always checking, and we are checking mi and ri. Cannot unpack, maybe there's an error. An error here, because numerate is this the problem? Let's check. So the sun's position is like 0, 77.9. What's the actual measure here? Is distance from the sun is 10 to the power of 6 kilometers. Okay, so and this is our last one for the last planet, Pluto. Okay, which it's like non-contributing quite a lot, like the moon have a small mass. Okay, so it's working. So this is the numerator, the first sum, and the second sum 2, the denominator, plus equal mi. This is the sum of all the masses. So actually, our center of mass is sum 1 divided by sum 2. Okay. Okay, and we have this result here for the center of mass, which is in terms of 10 to the power of 6 kilometers. Okay, 1.5 to the power of 6. Right. Okay, let's print this center of mass normalized in terms of solar diameter. Diameter of sun is this is the sun's diameter, which is like some Wikipedia. This is the diameter of the sun, which is in our units is 1.39, like 0.14, something like this. Okay, so divided by ds, this is the normalized. Let's actually make some actually maybe too cumbersome. It's working. Okay. This distance is like 1.08. So I'm not an expert, so actually I'm not sure if this is correct, but what this very simple script is telling us is that if this is the sun, this is the sun, this is the sun diameter, okay, the sun diameter, which is this diameter, so the radius, of course, is the half of this. If this is the diameter, 1.08, it's like we can approximate to 1, so it's like 2. So if we raise this one here, okay. So what we are telling is that this distance between the solar center and the center of mass, is actually a bit more than the diameter of the sun. Okay, it's like here. It's more than double the radius of the sun. So it's actually outside the sun by twice its radius. Let's return to our script now. Okay. Now let's consider only Jupiter and Neptune. Okay. Now we consider only these two planets in the solar system. All the others are discarded. Okay. So Jupiter, no, actually Neptune. Yes, not Neptune, but Saturn. Only these two planets, because they have most of the mass. Also Neptune is Uranus is very massive, but these are the biggest in terms of mass. Okay. These are, of course, the 6th and the 7th. So the center of mass is R0, and 0, of course, we are considering the sun is the most massive, plus M6 times R6, this is Jupiter, plus M7 times M7. Let's see, it is right. 1, 2, 3, 4, 5, 6, and 7. Jupiter and Saturn. Okay. Divided by the sum of the masses, mass of Sun plus the mass of Jupiter plus the mass of Saturn. Okay, and let's print our newly found cm over the sun diameter of the sun. Okay, so if we consider only these two planets, our result is a bit lower, of course. We are considering only two planets, and in the first calculation we have all the 10 planets. But like if this is like 1, this is almost like the 65%. So of course, since they have a really big mass, they contribute a lot. If we consider also Neptune, okay, we have to sum also for oh, well, actually we have an error here. Spot. This is R, of course, not M. Okay, so it's not okay. This was not 65%, but 83%. So they contribute a lot in the previous calculation. So the main contribution about the offset of the center of mass from the center of the sun is mainly because we have two really big planets, which are Jupiter and Saturn, and their effect is to shift the center of mass outside the sun. If you consider also Neptune, which is R, of course, plus M times R, and Neptune is 1, 2, 3, 4, 5, 6, 7, 8, 9, the 9th planet here. We have to sum also all the masses, mass 9. We found that it's even closer to 1, so it's 99%. Okay. So, of course, it's not Earth or Moon, as we said before, that contributes to this offset of the real center of mass compared to the center of the sun. But are these big planets here that contribute more. Of course, also Uranus, if we include also Uranus here. This value here, it's like more is closer to 1.08. Of course, this reasoning is very approximate. This is a limit case where all the planets are aligned. So the actual center of mass is we can consider this center of mass in a point between okay. Let's actually have this circle here with a radius of 1.08 the sun's diameter. Okay, and this is the limit circle. So the center of mass is inside this circle here. Okay, we can expect the center of mass in this circle here, where it's more likely that it's like near the center of this circle here, and is very unlikely that is on the outer edge of this circle, because when the center of mass is on the circle, on the limit circle, it means that all the planets are aligned in some direction. Now we have taken the horizontal one, but they might be aligned also in this direction, of course. And this concludes this very simple video, actually quite useless. Thank you for watching and stay safe.